In our last lecture, we examined two different ways that signals could be made simple: averaging and sampling. Let's just review what we learned on averaging. We found that the average of a signal y of t over an interval from t1 to t2 could be obtained by taking the integral from t1 to t2 of 1 over t2 minus t1 times y of tau d tau. You'll note this averaging process yields a scalar coefficient, not a signal. When we multiply it by the basis function, we generate a signal. That is how we created the approximate signal ya of t from y of t in our last lecture. In this lecture, we'll learn about a different kind of averaging process that takes the signal y of t and produces a new signal from it. So this new kind of averaging is a system all by itself. When we do the averaging, we lose information in the signal. But in this case, the type of averaging we're discussing today, moving averaging, can actually provide greater insight into the behavior of the signal. It does this by removing random fluctuations or noise from the signal, so as to reveal the underlying trend. Moving averages are very common in stock market analysis. So here you see the moving average signal for the stock price of Google. And the top line that's more jagged is when the average is taken over 10 days. The bottom line, which is smoother, is when the average is taken over 50 days. The trend lines of such moving average curves are viewed as more representative of what the stock is actually doing than the individual day-to-day fluctuations. The question I now want to address is, given a signal, how do we generate its moving average signal? So here is how that signal is generated. So we're given an initial signal x of t, and we want to generate the moving average signal, which we'll call y of t. And I want to find the moving average signal at a particular time. Let's call it t1. So the moving average value at time t1 is found by finding the average of the signal x of t over the last capital T seconds. To do that, we'll find the area under the x of t curve from time t1 minus capital T to time t1. We find the area under the curve and we divide it by the duration of the averaging window, capital T. Now imagine doing that operation of finding the area under the curve over the last capital T seconds and dividing by capital T, and doing that for each and every time. If we do this for each and every time, this will generate a new signal, and this signal is the moving average signal, y of t. This can be mathematically expressed as an integral. Y of t is the integral from t minus capital T to t of 1 over capital T x of tau d tau. This is a system description because it takes a signal x and produces another signal y. If we define a function f of t, which is a pulse that is 1 over cap t high and is non-zero from 0 to capital T, then we can write our moving average in the following fashion. We can say y of t is the integral from minus infinity to infinity of f of t minus tau x of tau d tau. Now I want you to note that while this may look a lot like our circle product, in fact it's not the same. And the reason why is that the argument of f is not tau, but t minus tau. This type of integral is what we'll later learn to call a convolution integral. This integral is a system. It's a relationship between an input signal, x, and an output signal, y. Let's now examine how this moving average system responds to a high-frequency input signal. So here's x of t. and the frequency is high in comparison to the window capital T. So there's many oscillations of x of t during capital T seconds. This means the positive and negative areas under the curve will tend to cancel out, and therefore the output y of t, which is the moving average, will be much smaller in amplitude than x of t. So you can see the moving average system tends to remove high-frequency fluctuations. Now let's look at the behavior of the moving average system when we have a different input. Suppose the input, x of t, is the sum of two signals. There's a low-frequency signal, v of t, and a high-frequency signal, w of t. What will the moving average system do with this input signal, x of t? What will y of t look like? In this case, the output will look just like the moving average of the slowly changing signal, v of t. W of t will be removed because its fluctuations will be averaged out. This is easy to show mathematically. The moving average y of t is the integral from t minus cap t to t of 1 over t x of tau d tau. We substitute in x of tau equals v of tau plus w of tau, and we break the integral up into two portions. The second portion, which is the average of w of tau, will be approximately 0 for the reasons we specified before, while the first part is the moving average of v of t. Let's now look at some signals and their moving averages. In the first examples we'll look at here, capital T is equal to 1, so we're doing an average over a duration of 1 second. We have signal x of t on the left and the moving average signal y of t on the right. In the first case, x of t is a pulse of width 2. Now this width is wider than the moving average window duration, capital T equals 1. As a result, the moving average signal achieves the same maximum value as x of t. In the example at the bottom of the page, the x of t looks just like the one above, except it's been shifted to the right by 1 second. And you'll note that the moving average looks just like the one above as well, except that it has been shifted to the right by 1 second. This is a general property of the moving average system, that it commutes with a shift operation. We'll now look at some examples where capital T is equal to 2. In the first example on this page, x of t is the same as it was on the previous page. You'll now notice that y of t is different because we're averaging over 2 seconds instead of 1. In this example, the averaging time, capital T equal to 2, is exactly the same as the width of the pulse, x of t. As a result, the moving average achieves the same maximum as x of t. In the example at the bottom of the page, the width of the pulse duration is 1 second, and this is shorter than the averaging time, capital T equals 2. As a result, the moving average does not reach the same maximum as x of t. I would like you to verify that you can find these moving average signals for all the examples that we've discussed. The moving average system we've been discussing is referred to as the causal moving average system. This is because we determine the moving average by finding the average over the past capital T seconds. That's how the moving average for time t1 is determined, by finding the average between time t1 minus cap t and t1. But there's another type of moving average, one that uses future information as well as past information. This is referred to as the non-causal moving average. Here's the equation for it. We determine the non-causal moving average y of t by taking the average of the input signal x of t from time t minus capital T over 2 to t plus capital T over 2. So you'll note that the output at time t is dependent upon future values of the input. It does seem rather strange that the current value of the output can depend upon future values of the input. It seems strange because we know the input is what causes the output, but here the cause of the current output is something from the future. Nevertheless, we can define such a mathematical relationship, such a system, and we can study it. We'll discuss later causal and non-causal systems. For now, let's just examine these two different types of moving average. Let's start by looking at the output of the causal moving average system and the non-causal moving average system when we put a pulse input into the system. The pulse input is shown on the left, x of t. It has a height of 1 and a width of 2 seconds. The moving average in both cases is done with a moving average window, capital T, equal to 1 second. The causal moving average begins to move up at 1 second and plateaus at 2 seconds. Then, starting at 3 seconds, reduces back down to 0. And at 4 seconds, the signal is 0. For the non-causal moving average, you note that it starts to rise up before the input signal goes from 0 to 1. It also starts to decrease before x of t moves from 1 back to 0. These are both signs of the non-causal behavior of this moving average. I'd like you now to look at the center of the waveform for both the input and the output. The center of the x of t waveform is at 2 seconds. For the causal moving average, the center has been shifted. It's now at 2.5 seconds. For the non-causal moving average, the center is at 2 seconds, which is the same as the input. Let's now look at an oscillatory input to our causal moving average system. The input x of t is a square wave. It alternates between +1 and -1 with a period of 2 seconds. The moving average output is shown below, and this is the causal moving average, and you'll note that there is now a difference between the phase of these two signals. A half-second difference. That is, the center of the peak of y of t differs from the center of the x of t waveform. This is referred to as out of phase. The output y of t is said to lag behind x of t. That is, x of t peaks first, and then y of t. When we look at the non-causal moving average, we'll see the situation is quite different. These signals are in phase, because the peak of y of t is aligned with the center of the peak of x of t. This in-phase characteristic means that the output moving average y of t more closely resembles the input x of t at any given time. Thus, the non-causal moving average can eliminate noise or fluctuations in the signal that are at high frequency and still represent what's going on at low frequency in a more accurate fashion. If we had access to future values of a stock's price, we'd certainly be able to make more accurate decisions about what to buy and what to sell. So I think you'll agree that non-causal systems do have some obvious benefits. So we've touched on some important ideas in this lecture and the previous one. The first is, whenever we simplify a signal, we reduce its information content, and therefore we cannot reconstruct the original signal from the simplified signal. Particularly, we've looked at averaging, both averaging that is a moving average and also the stationary average of the previous lecture. In the moving average case, we've examined both causal and non-causal moving averages, and we've seen the different kinds of behavior that they display.